Hello, I'm OurSync, creator of World Fabric, which is a game/metaverse engine that can automatically synchronize arbitrary running code over the internet. It also warps time around players to hide latency and reduce load, also mostly automatically. I call the algorithm relativistic synchronization, and in this video I'm going to talk about the problem of video game networking in general, what motivated a different approach, and how the new algorithm works. Before I get into anything technical, let's take a step back, way back. What are we trying to do when adding online multiplayer to a video game? What is the goal? Ideally, when players interact with the virtual world, the exact same thing happens at the exact same time for all players. Unfortunately, due to latency caused by the physical limits of reality, the only way to have everyone see exactly the same events at exactly the same time is to delay the effect of player actions long enough that data describing those actions can reach all players before the action happens. Obviously, this is no good for a real-time game. It would feel awful to have your basic movements delayed by the maximum ping on the server. So we also have a second goal, responsiveness. Ideally, the actions taken by players will be reflected in the world the instant they are taken. These two goals, synchronization and responsiveness, directly conflict with each other. So in practice, we have to bend a bit on one or both goals, and that is where things get interesting. Let's consider a simple example of two players throwing a ball back and forth. Player 1 on the left throws the ball to player 2 on the right, and then player 2 catches it and throws it back. We can't keep the players perfectly in sync though, so there will actually be two versions of events. The one the left player sees, which I'll put on top, and the one the right player sees, which I'll put on the bottom. This is what it looks like in an ideal world, the same. But for the next example, let's set the ping to 2 seconds. Which is unrealistically high, but it makes it easier to see what's happening with different algorithms. Ping is round trip, so it's 1 second one way, and I'll add little blips to show the packets moving as well. One simple approach is to have one player be the server, which is the source of truth, and all others be clients. Maybe clients don't even run the game and the server just sends updates about the game state regularly. This will make the game very responsive for the server, but if clients rely on the server for executing their actions, then their response time will be the full round-trip ping. Sending full game state is also a lot more network traffic than sending just player inputs. That very high latency for the client feels bad, so what if we let players be the source of truth for themselves? For our ball example, let's say the source of truth for the ball is the last person to touch it. This looks the same as our client-server example until the ball reaches player 2. With this approach, player 2 can throw immediately, but now player 1 won't see it until later. That works fine for the simple example, but what happens if there are two balls and they hit in the middle? Maybe one player sees them hit and the other doesn't. Which version of reality is true when two objects handled by different players interact out of sync? This approach breaks down for complex games with any kind of physics, and likely devolves back into a designated server being the source of truth, with the sole exception that clients own their own player characters. Still, an improvement where you can get away with it. But can we do better? The next logical leap is realizing that an event can be made to have happened before the network packet for it arrives. What if we build our game so it runs like clockwork? Each frame of our simulation is generated deterministically from the frame before, and all of our players move through the simulation in lockstep, producing identical results. If we keep the history of those steps, then when we get a packet with an action that happened earlier, we can roll back to a past frame, inject the action, and then run the simulation back up to the current time to get what would have happened had that event been input when it happened. Let's see what that looks like. This one is a bit weirder because we get these jarring jumps when a packet arrives that causes rollback. Suddenly a ball that was being held was actually thrown 1 second ago and is already well on its way. Overall though, this is a much better result, being exactly in sync for most objects most of the time, and it works for arbitrarily complex logic like physics simulation. From a purely numerical standpoint, this is as good as we can do for synchronization, short of predicting player actions before receiving them. But intuitively, these visible jumps don't feel as in sync, because they don't follow the expected rules of the simulation. Balls don't teleport. Having something that is numerically out of sync more, but behaves closer to how we expect the simulation to behave, would in practice feel better. common approach for solving this problem is interpolation. The idea is simple. When we get a situation that would cause an object to teleport in a way that's physically impossible, we instead slide along a line, or interpolate, between the old position and the new position over a few frames. It can still look pretty unnatural, but it's usually enough to make the retroactive corrections not catch our attention. Less jarring, but still moving in a way that isn't quite right. Everything I've discussed up to this point is standard-ish practice. Lockstep with rollback and interpolation is more or less the gold standard for real-time video game networking, but it's not without drawbacks. The biggest issue is processing load. If you have events being injected into the past constantly, then you're constantly rerunning previous frames. It's not impossible to end up calculating a frame of game logic 10 or more times if you're not careful. If you're making a fighting game with only 2 characters on screen, then this is fine. But games with more objects may have to simplify and really optimize their logic or reduce their game's internal tick rate. Some games delay actions and do lockstep without the rollback. Other games have custom logic to limit rollback and rerunning to only affected objects or systems. The other issue is what I was just talking about with interpolation. The way that rollback naturally appears is jarring, and simple interpolation can still look off. Custom game logic might be required to smooth things out. So can we do better? For World Fabric, I wanted something that just worked out of the box, could handle thousands of physically simulated objects in real time, and required minimal extra game-specific work to look good. I also wanted to be able to run multiple unrelated apps together, so I didn't like the big fixed discrete steps that come with lockstep. I created an algorithm I called timeline synchronization, which was very similar to lockstep, but instead of moving in large discrete steps, events occur at specific times on a timeline. It tried to reduce the load of constant rollback. I built a system that would automatically track what events on the timeline read which objects, and then I could do selective rollback. If an object got rolled back from a network event, I could figure out how that data propagated through the program and only rerun those parts. This dropped the rollback CPU load to practically 0, but it was moot because tracking every read and write on every event to be able to do this selective rollback cost more than just running my app 10 times. So is there a way to do selective rollback without game-specific logic or logging every data read? In the real world, there is a maximum speed, the speed of light. When we look out into space, we don't see objects as they are, but as they were in the past. In relativity, every event has light cones that tell us the causal relationship to the world. Objects can only be affected by events in their past light cone, and they can only affect events in their future light cone. So that's what relativistic synchronization does too. In World Fabric, every world has a maximum speed of information and a minimum event duration. When an event reads an object, it gets it with a speed of light delay, and when an event writes data, it is guaranteed to take at least so long before the data becomes available for reading. Additionally, the timeline itself is run with a vantage point, so events far away from the local viewer aren't even run if they wouldn't be visible yet. Other than that, it's basically the same as lockstep with rollback. Just instead of maintaining lockstep, it uses these restrictions on the flow of information to enforce a much weaker constraint of causal consistency. Causes must precede their effects, but otherwise events can run in arbitrary order. But without further ado, here's what that looks like with the ball example. The ball appears slower for each player when moving away from them, and it appears faster when moving towards them. So player 1 throws the ball, and they see it begin to move immediately. Then player 2 gets the packet to see player 1 throwing the ball, and they see it begin moving much faster. Player 2 sees the ball reach them and throws it back, and player 1 gets that packet before player 1 sees the ball even reach them. So in this example, there's no rollback necessary. The game is instantly responsive for both players, and the ball travels on its true path exactly for both players, with the only difference being speed. For objects that are too close together for the time warp effect to completely hide the latency, the behavior to close the gap looks similar to regular lockstep, and you can do interpolation as well. But even in that case, the CPU load is dramatically lower because only other objects that are close to the event will get rolled back. In general, relativistic synchronization only performs rollback for events which are in the future light cone of the injected network event, and also in the past light cone of the receiver's vantage point. The practical effect is that you can have many players injecting events slightly into the past every single frame, and not have to worry about it. This approach scales well to arbitrarily complex interactions as well. Use another demo with a bunch of bouncing balls. The blue player sees the left, while the red player sees the right. If you look quickly back and forth, you can see one scene is ahead in time in the top left corner, while the other is ahead in time in the bottom right corner. But if you just look at one side, it's nearly impossible to see the time warp is even happening. Now you might say, 2000 ping is unreasonable. You're exaggerating to make problems more noticeable. And yeah. So real quick, here's the same sequences with 300 ping, which is still bad, but more likely to be seen in the real world. Client-to-client ping is effectively additive, so you can see delays like this connecting US to Japan or London. In this case, it's harder to see the lag, but most people will still feel it when playing a fast-paced game. For indie games, the choice of what approach to take for networking likely comes down to ease of use and performance. So I built the system using template metaprogramming to automatically wrap arbitrary C++ objects and functions at compile time to be synchronizable in World Fabric worlds. There are some restrictions, but it's pretty nice to work with so far. I'm currently developing a simple game called Narball using this technique, and I'll make another video about that and what using World Fabric looks like in practice soon. On the performance front, things are pretty good too. There's a certain amount of overhead from retaining the history, doing the speed of light delay on reads, and checking when events are allowed to run, but it's predictable and doesn't grow with the number of players or spike when lag increases. The client version can get into the low thousands of synced physics objects without doing anything especially clever on the app side. I expect speed to improve over time, in particular, because of event timing restrictions, events don't have to be run in a strict order. Functions are run in causally independent batches, and it should be straightforward to parallelize these batches. If I could get the engine to automatically parallelize app code, I might be able to completely offset the overhead. I won't really know what's possible there until I try, though. I've also got ideas for a horizontally scalable version of relativistic synchronization for open-world MMO type things, but that's early stages. I'm going to work the kinks out of the basic version and open source it first. There's so much more to be said than fits in this YouTube format, so feel free to reach out if you're interested in using or duplicating this tech for your own games. Until next time, our sync out.